Good day. So today we will be talking about sensors and transducers. So the objectives of this study is to describe the different sensors and transducers in extant biomedical devices and explain the principles of how they operate. So we first define what is a sensor. A sensor is a device that is used to detect a certain signal, hence the name sensor, sense. So it often forms a part of a transducer. A transducer converts one type of input signal, such as ionic current, mechanical vibration, absorbed light, or chemical reaction, into another form of output signal. Hence, it transduces or transforms signals. Now, we have micro-electro-mechanical systems or MEMS devices in extant biomedical devices. So, the advantages of the MEMS-based sensors are they are small size, high sensitivity, high accuracy, high precision, and low power consumptions. So, these devices are usually used to measure temperature, fluid or blood flow, pressure and accelerations, and among other parameters in a biomedical system. So the small size of MEMS devices is an advantage for biomedical applications because they have short response times, which is actually quite important. It is very important in order to detect fast or rapid changes, especially the human body is a dynamic system. It's very dynamic. So in order for the device to keep up with the changes of the system, it's actually a good idea that having these MEMS devices with a small, short response time because of their small sizes. So they can be made of biocompatible substrates such as PDMS or polydimethylsiloxane, in addition to other materials such as silicone, polyethylene, and other inert compounds. Now, especially for biomedical devices, the compounds, the activity of the compounds when they interact with the biological environment is highly important because whether there might be a possibility of adverse reactions or adverse immune effects, especially for devices that comes into contact with the body. So the dimensions of these MEMS devices range from micrometers up to several millimeters. So here is a schematic of a formation of your PDMS, a PDMS device. So usually these are found in microfluidics. So you have your silicon wafer and you add a span photoresist layer. You use a UV dark field mask to actually have impact holes in your wafer, and then you pour your PDMS and then bake them. So this device, the PDMS will therefore have a certain configuration. This is the surface configuration of your PDMS device. So this is actually casted on your wafer. So and then another way of manufacturing devices is you have your glass slide coating. And again, you have your photoresistant material here. You put a UV mask where you will have your um, device in a particular design or architecture, and then you bake it and then remove the photoresistant part. So basically, this is the structure for your PDMS device. So an example of a MEMS sensor here is in contact lenses. So this is a circular active outer ring. So if you notice, this is your contact lens, and then this is, there's a MEMS device here. So this device is used to measure the corneal curvature when in response to intraocular pressure. So this is usually used to test glaucoma. Patients with possible glaucoma. So the activity of the eye can be measured here. The intraocular pressure, the pressure inside in the eye. So this is from Sesame Triggerfish, which is the manufacturer of these contact lenses. So in sensors, and especially in biomedical devices, noise is inevitable. So there are two basic components of instrument noise in biomedical devices. You have the external noise, usually comes from power lines, which is coupled into the measurement system, and the intrinsic noise, which the intrinsic noise of each component in the measurement device. So, in terms of noise, the overall noise level determines the smallest quantity or the sensitivity of your instrument. So of course, especially when you remove the noise, the simplest way to remove the noise is actually um, differentiating into actual signals. So you get the basal noise level and then remove it. That's the simplest, one of the simplest way in removing noise. However, if your signal has the same amplitude or strength, signal strength as uh, your the thing that you are sensing, the parameter that you are sensing, your instrument might be less sensitive. So, a large noise will negatively affect that sensitivity of your instrument. So, having lowering the noise level makes your sensor more sensitive. So there's are some types of noises. You have the thermal or Johnson or the Nyquist noise, which arise from temperature-induced fluctuation in carrier densities. The shot noise caused by the random arrival time of electrons or photons. You have the flicker noise, which occurs due to variable trapping and the release of carriers in conductor. The phase noise in high-frequency RF system, such as those used in a wireless implanted device. Uh, although wireless implanted device are not that common, not much. Anyway, this arises from instabilities in oscillator circuits, whereas mechanical noise, an example of a mechanical noise is in the Brownian motion. This affects the Brownian motion effects on the proof mass in an accelerometer. So Brownian motion is the random movement of your molecules. So let's talk about the different types of sensors. So we have here your voltage sensors, usually in biopotential electrode. You usually find them in ECGs devices, electrocardiograms, EEG, electroencephalogram, EMG, electromyogram, and EOG devices. Actually, it's in the tip of my tongue. I forgot the EOG. Anyway, these electrical signals measured by electrodes on the skin surface arise from action potentials that occur at the cellular level, and they set up ionic current paths within the body. So as voltage sensors, they measure basically the voltage potentials. It you might not, especially for say ECG. ECG devices usually see them they are placed on the chest area and then the arms and the legs. Now, although when we touch them, we don't really feel any electric currents. That's because the electrical currents in our body are very, very small to be detected by us. Now, that's the thing with voltage sensors for biomedical devices. They must be sensitive enough to actually sense the ionic currents in the body. And remember, the carbon-based systems, such as our body, are resistors. They do not really transmit electrons that well. So anyway, so anions and cation concentrations inside and outside the cells at rest. So what's the issue with the ion and cation concentration? So because we are here looking at ionic currents, we are sensing voltage, we are sensing the current here. Current is a moving charge. So the sources of the charge, the movement of charge inside the biological system are the ions, the dissolved ions in the aqueous environment. So in the cell, you have the sodium ion concentration of 12 millimolar, and outside the cell, it's 145 millimolar. For potassium, you have 155 millimolar, and outside the cell, this is um, 4 millimolars. So for chloride, it's 4 millimolars inside and 120 millimolars outside. So if you look at these values, you can see that there's a really large difference, especially look at the potassium ion concentrations. So you have a large difference inside and outside. And because of these differences of the concentration of the ions inside and outside the cell, there is a membrane potential. So it generates an ionic a membrane potential in the ions, and the differences in the intracellular and extracellular concentrations. This concentration is your at this is for a cell at rest. We call it resting potential, the difference across membrane. And we call it a resting potential because these are usually found in neural cells. When neurons are not firing, that means they are at rest. So that's the resting potential. That's the normal potential. But when they become activated or they are firing. So if you remember from your physiology lessons, the potential, the movement of electric current across the axon body towards the from the dendrites to the axons in your neuronal cells. So when the cells, there's no current happening, so at rest, there's nothing much happening. The nerves aren't firing. It's a resting potential, and this is their equation. So when it fires, there will be drastic changes in their concentration, and that's actually what generates the ionic current paths that are being sensed by these instruments. So using the concentration, because again ionic concentration, so how will we relate the current, the potential, the voltage membrane, the membrane potentials using our concentrations of ionic current? Actually, here is the Goldman-Hodgkin-Katz equation, which is actually used to calculate the voltage, the potential, the membrane potential from the data of the concentration of the ionic currents inside and outside the cell. So here, our membrane potential is equal to RT, R as the gas constant, T is the temperature in Kelvin, and F is the Faraday's constant. Actually, this is derived from electrochemistry. And then ln of the differences in concentration outside and inside. So just add all of the ions and its permeabilities. So when we talk about permeabilities, that's because the membrane is quite leaky. So when we say leaky, there are channels in the membranes that spontaneously open and allows the ions to pass through. So the permeability here means that probability, the likelihood or the chance that this potassium ion that are outside will permeate to the inside of the cell. So that's the leakiness of your membrane. So that's the permeability of your membrane. So it's not solely the actual value of the concentration inside and outside, but rather you also need to consider the leakiness of the membrane, because sometimes channels spontaneously open and allows ions to pass through. So to cross from being outside to coming inside. Now the values for permeabilities, these are the values for your skeletal and cardiac muscles. And that is why if you plug it in the equation, using the values of the concentrations here, you will see that the resting membrane potential E will have a value of negative 85 millivolts for skeletal and cardiac muscle cells. So in contrast, this is negative 70 for your neuronal cells. So there's a slight difference in their resting membrane potentials. So just a brief review. So you have here your nucleus and your basically sorry, this is your neuronal cell. So a typical motor neuron. So you will see here the membrane potential will enter from the dendrites to the axons. So the changes in the concentrations here. So in terms of over time, you have the changes in the membrane potential, and you have if you look at if you're looking at the permeability. So the permeability of sodium will peak here, and you will have a potassium permeability will peak at around this time. So basically, it reflects the order in which the ions, the channels open in the neuronal cells. So the channel opening will allow the ions to pass through from outside to the inside or inside to the outside to equilibrate the large difference in the concentration outside and inside. So this is your membrane potential. So when neurons fire, you will see here from a negative 70 or negative 80 area around this region, it will be depolarized. We call it will become it will approach zero and then actually go over a bit. So we call this one the polarization. And then by the actions of the pumps to go back to the, it goes back to the resting potential. So it will go back to the negative resting potential value. So this is the graph here shows the permeability of the ions. So that means here at peak permeability, that is the time when the sodium ions are fully open. And this is the peak permeability for potassium. That's when the potassium ion channels are fully open. So basically, that what triggers the depolarization is, or rather, what drives the depolarization is the opening of the sodium ion channels, followed by the potassium ion channels. So the polarization and repolarization processes in a cardiac pacemaker cell. So you have T for transient channels opening and L for long lasting. So here, when we say transient opening, these are what I talked about with being a leaky channels. So it's transient. So it spontaneously open for a short period of time, a very, very short. It allows one or two ions to pass through and then shut down. And then for the long lasting opening, it is in response to actual potential, cell potential, or the firing of your neurons. So at long-lasting opening, it will really drive the depolarization to a positive value. And then, after that, the pumps will act on. Actually, the opening of the potassium channels will negate the charge to go down until you go back to the resting side. So the transient opening here shows the leakiness of the membrane. So another view here of the polarization and repolarization process in cardiac ventricular cells. So you have here around the negative 85 and then an immediate increase, this for cardiac ventricular cell, and then a slower decline. So this is driven by the movements of the potassium and the chloride and potassium ions, and even some calcium ions. So the movement of those membranes allows because initial influx, very fast influx of sodium, and then the slow efflux of the other ions will decrease the membrane potential back to negative 90. So what are volume control fields? So volume control fields refers to body parts through which ionic currents propagate. So remember, we are looking here at the voltages. Voltage sensors seek to sense or measure voltages in the body. So the target here are, especially for say ECG or even for EEG. EEG is much more difficult because the sensors, uh, uh, the the sources, the electrical sources here, which is the brain, the neurons in the brain, are protected by layers of tissue, the glias, and then you have the skull, the bone in the bone skull, and then the scalp, and then even the hair. So it's actually quite a challenge to develop a very, very, very sensitive voltage sensor. For that, sometimes it actually requires people to shave off hair just to measure the voltage current in the head. Now, the volume control fields are the body parts through which these currents must pass through for the sensors to sense them. So in the case of the EEG, so the volume control field is heterogeneous because it has the tissues, the blood, the cerebrospinal fluid. It also must pass through bone, and then the scalp, the skin tissue in the scalp, the hair. So that's your conductor field. Sorry, not volume control, volume conductor fields. Now, in some cases, it's much easier. So, say for example, for the heart, actually, it's quite difficult also in the heart. So, we have here different models for propagation and its effects on tissues. So, the simpler models initiates a more homogeneous tissue type, but more realistic real-time models involves the non-homogeneous models, because again the majority of the effects here, or the volume conductor fields, the tissue between your source, the voltage source, and your sensor are actually a lot of different tissues. So I already discussed about the brain. How about the heart? When sensing the cardiac muscle, the cardiac cells, the voltage, the conduction in the cardiac cells, it remember, it's in, of course, it's in the heart. So what is between your heart and your electrode sensor? So it's basically, of course, the tissues in the heart, the blood from the tissue surrounding the heart, the rib cage. Although although as a being a rib cage, so there are areas where there is no occlusion of your say the bones. But again, you still also consider the bone in the ribs, and you have fats, especially for females. So it's on the left side of your sternum. So it's on the left breast. So there's on the breast region, of course, they have the muscles, and for women especially, you have fatty layer tissue there, and of course your skin. So that those are really homogeneous or different types of tissue. So depending on the type of tissue, the propagation might be different. So the conductor fields model, they try to explain or use to model the link between the microscopic electrical activity generated within a bioelectric source and the macroscopic potential distribution produced at the surface of the body. So again, the different models, we usually apply these models the to calculate and actually design our sensors. So we have two basic components. Of course, your bioelectric source. For the case of the heart, it's the cardiac muscles. And the conducting medium, which also is an electrical load because again, it's a carbon-based tissue. They are generally non-conducting medium that is actually forced to conduct these electric currents. So here is an illustration of the propagation of ionic currents produced by a depolarization wave spreading via the heart. So if this is the cell in the cardiac cell in the heart, so the polarization. So at resting condition, and then when they depolarize, of course, there's a movement of electrical ions. So the movement of these electrical ions, it must propagate through this tissue that stands between, of course, your heart and the electrode. So the polarization spreading by the heart through a homogeneous medium. So this here is a homogeneous model. Through a homogeneous volume conductor and the corresponding surface biopotential measured as surface electrodes. So here are your surface electrodes. So here is a positive electrode because the propagation, positive to negative, so there's an excess of positive here, excess of negative on this region. So another look at the potential layer. So you have here an electrical circuit model of your body skin electrolyte electrode system. So this corresponds to the transduction of ionic currents in the body to an electrical signal from the electrode. So here you have the electrode and then an electrolyte gel. So in using gels, actually it's very important or very helpful for electrodes to they have gel because it serves a variety of functions and it helps in the sensing as well. So you have the epidermal layer, the skin, and then the inner layer of the skin, your dermis, and the subcutaneous layer, and the actual body part, which is the source of your current. So uh, this is your electrical circuit model. This is another volume conductor field model, which considers the differences in the tissue types layering between the electrode and the source of the current, which is the body. So here you have your half cell potential, and then RE and CE. This is the electrolyte gel interface, and you have your resistance from the gel electrolytes, the resistance, uh, uh, the gel skin interface, and then you have resistance and conductions from your epidermal layer and resistance from the dermis and subcutaneous layer. So here are illustrations of some ECG electrodes that are in current use. Actually, this one is one of the things, the easier clip-on ECGs, and another, this one is usually attached to the body. So you have here these small balls. They serve as suction pumps that suck in, air, of course, and allows them to actually adhere to the skin through suctions. So here is the electrode, a disposable electrode with a gel inside. So it allows the electrode to actually stick. So the electrode usually used are silver chloride electrodes. So here is your silver chloride electrode, and you have here a gel, an electrolytic gel, which is quite a very helpful addition in the sensing. So this is actually this instrument here, cross-sectional, and how attachment to the skin. So you have here the adhesive layer. Now, the electrolytic gel, as I talked about, they serve several purposes. So, first, it enables the transfer of charge from tissue to the electrode. Then, it also increases the actual contact area between the skin and electrode. And because, of course, our skin is not a smooth surface, there are, I'm not saying that your skin is naturally not smooth, but microscopic, if you look at the microscopic image of the skin, there are, of course, pores and holes in there. So, having a gel increases the actual contact area, and it also uh, reduces, or rather increases, reduce the contact impedance. So it also diffuses to the skin, which can further reduce the contact impedance, and allows minor movements of the electrode without actually loss of contact of the cell. Without loss of contact to the skin layer. So that's it for your voltage electrodes. So on the next, we will talk about optical sensors.